Welcome back. Today we're taking a look at absolute value functions. We've seen absolute value before, back in ninth grade and a little bit of this year. We've solved absolute value functions, we've plugged stuff in, and we've even taken a look at a number line. Today we're going to be graphing absolute value functions. So we're going to take the same standard as before, taking an absolute value function, expressing it symbolically, and showing key features of the graph. As we know, the absolute value function takes a look at how far away a number is from zero. It's the absolute distance. So, as our definition, numbers inside of the absolute value bars turn positive at the end. So if we were to take this function, the absolute value of x, which we call the parent function, we could input different numbers. So the absolute value of 3 is just positive 3, while the absolute value of negative 4 is positive 4. Again, we're taking a look at how far away a number is from 0. Think of it in terms of distance. You can't go a negative distance. So in this case, it's still going to be 4 instead of negative 4. What this means in terms of the picture of the graph is we end up having a V shape. It's similar to a quadratic, and we have a maximum or a minimum, but instead of a curved sketch, we actually have straight linear lines. These linear equations go left and go right, forming our classic V shape. While we do have a set process of how to solve these, essentially it just equates to plugging numbers into an X, Y chart and then graphing our V-shaped graph, and then labeling our domain and range. So let's take this example, for instance. We have this example and then one more. In this case, we have our x's all the way filled in. We simply need to plug those into our function and output a y value. We take the negative 3 times the absolute value of negative 2. We simplify this a bit. The negative 3 stays the same, but the absolute value of negative 2 is positive 2, giving us a final answer of negative 6. We do the same process, just now with x equals negative 1. Take negative 3 times the absolute value of negative 1, which is the same thing as negative 3 times positive 1, which gives me negative 3. Following the same process, we plug in the 0 to get 0. We plug in 1 to get negative 3. And we plug in 2 to get negative 6. What we should notice here, just like we had with quadratic equations, we have symmetry. That's because we have a minimum or a maximum value in our V-shaped graph. Go ahead and plot those points, and then we'll worry about domain and range here in a second. And the last ones are negative 2, negative 6, and positive 2, negative 6. And we have our V-shaped graph. If we look at our domain and range now, again, domain is the x values you can plug in, range is the y values you can get out. So, domain-wise, you can plug in any x value you want. Again, making x all real numbers. For the range, however, just like we did with quadratics, we have a minimum or a maximum. In this case, we have a maximum value, which means y has to be less than or equal to whatever the maximum value is. In In this case, it does not go any higher than 0. And this right here is a pretty classic example of an absolute value problem. As we get ready for our last example, we see that we have actually a larger XY chart. The reason for this is we want to show a little bit of the variation in these types of problems. Notice with this that the absolute value part is by itself, and we have a -1 on the outside. So in this case, we have a few extra steps we need to follow before we go right ahead and do the absolute value. And we'll kind of see what that means as we go through the first few. Just like we did, we're simply plugging in values in for x. Starting off with -6, we plug it in, and right away we have to do some simplifying in the absolute value. -6 plus 3 gives me the absolute value of -3 minus 1. We know the absolute value of -3 is +3 minus 1, giving me a value of 2. So instead of the previous problem where we simply plugged a number in, this case we actually have to do some simplifying before we get our final answer. So let's try it again. In this case, we're plugging in -5. And we get this as our initial input. We do some simplifying to get a -2 on the inside of the absolute value. Converts to +2 minus 1, which gives me 1. Doing the same process again, we'll follow through with that whole thing just one more time. Plug in the -4 plus 3, all minus 1. Inside the absolute value becomes a -1 minus 1. Again, the absolute value turns into a positive, and this would give me 0. Lots of straight lines in there. Sorry if that's confusing. If we continue this whole process, we're then going to get this is -1. For the next value, we get 0. For the next value, we get +1. And for the next, we get +2. Notice that the symmetry here for our minimum maximum is right there. So what we showed here was we have a larger XY chart, but we still centered the entire XY chart with the minimum or maximum. So go ahead over to our graph and plot these points. 4, 0, and -2, 0, -5, 1, and 1, 1, and 0, 2, and -6, 2. And we have our V-shaped graph like so. Final step. Well, in this case, domain, again, is all real numbers. You can plug any numbers in for x. Doesn't matter what it is, we can plug it in. For the range, same thing. Y has to be greater than or less than something. In this case, we have a minimum, which means y is greater than or equal to the smallest value, which is -1.